Hello, physics students. Yesterday we learned a very interesting thing, that simple masses with no moving parts, no chemical reactions, can act like a rechargeable battery. How? Well, I can take this mass and lift it, and that takes work with this hand. I put in a force times a distance, and I put work in to lift this. When I let this go, it falls and returns that work into my other hand. So rather than just hitting my hand directly and doing work on it like that with this hand, I could do it indirectly, put work in, deliver it through the mass. It's like a rechargeable battery, but this can do more work than just hitting my hand. I could hook it to something like a fan with an axle, and around the axle of a fan, and as it falls it could create wind, just like plugging a fan into an electrical outlet creates wind. Or we can use water falling, another example, in a hydro dam on turbines, and we can get energy, electricity out that way. So rechargeable battery simply by lifting a mass up. Today we're going to learn that there's another way we can store work to be delivered later, or energy, in other words. We can use a spring instead of lifting a mass. What I could do is I could take this end of the spring and I could put a force times distance. I'm stretching it out with my effort. So I put work in, force times distance. When I let that go, I get that force times distance, or that work right back. Put it in, get it back. Put it in, get it back. Just like plugging in your phone at night to recharge it and then discharge it throughout the day. So this is like another rechargeable battery storing work. So that's the topic for today, spring potential energy, PE spring. This diagram illustrates the concept of what spring potential energy is. Here's a spring. As I pull it and stretch it, I put a force times distance this way. So I put work in to stretch the spring. When I let that spring go, it snaps back with a force times distance. So the spring returns the work snapping back. Now, of course, we want to know the magnitude, the numerical size of how much work is stored in a spring. There's a formula for that right here. PE spring is 1/2 kx squared. And I just want to remind you, there's also another formula with springs, and students very often mix them up. In the force unit, we learn this is how hard a spring pulls, the newtons that it pulls back. This is the energy, the work, the joules that it stores when you stretch it. So also, again, I want to point out that these formulas are on the reference table. So here is our mechanics section, the last page of the reference table, the back if you want to call it that. So the first formula we learned in forces, F equals Kx, is right there. But right below that is the spring energy formula. PE spring is 1/2 Kx squared, which is what I have written on the board. Okay, so let me give you a minute to catch up if you need it. I'll pause the video for you to copy this down. Okay, now what I'm going to do is just a few examples to illustrate this formula at work. So here's example 1. A spring with a constant of 25 newtons per meter stores 18 joules of work. How far was it stretched? So we say, okay, joules, okay, so we know it's potential energy. We go to the reference table, we look up the formula, we write it down. And then we plug in the data. The energy, the joules, goes in for the PE of the spring. The spring constant is the K value. And then we solve for X. So what I did is divide both sides by 12.5, giving me 1.44 equals, that's what 1/2 25 is. And 1.44 is X squared. Take the square root of both sides, I get 1.2 meters. Now I want to talk about concepts also with a few more examples. So this is like a strict numerical example. I think this typically students are more comfortable with. All right, so let's look at a couple more examples. Okay, so example 2. Okay, so there is the example. Spring stores 20 joules of work if it's stretched 5 centimeters. How much does it store if it's stretched 10 centimeters? Now, this is kind of like a, I don't want to say proportion because then people set up a proportion and it doesn't work. But it's basically a question that very often appears on a multiple choice where you have to figure out by what factor the energy changes when I change from x equals 5 to 10 centimeters. And the way to analyze this, one way, is to look at your formula and see how x affects energy. And what you can see from the data is that x doubled. So x is now doubled in size. And you go over to the formula, right? 5 to 10 centimeters is a doubling factor. You go to the formula and you see how that would get affected if you doubled x. What would that do to PE spring? And some people say, well, okay, if you're doubling this, you're going to double that. And it's actually not true because of the squared. You could think of this formula as x times x, 1/2 x times x. And if we double this, we're actually doubling twice in the same formula. So what that means is that leads to a factor of a quadrupling of the energy. And so the new energy is 4 times 20 joules, or 80 joules. Okay. So let me give you a moment to copy that down if you'd like. Okay, so 80 joules, the displacement doubles, quadruple the energy. If you triple the displacement, you're going to have not triple the energy, but triple squared. 9 times as much energy if I triple the spring length. Okay, 9 times, or 9 times 20, 180. If I quadruple the displacement, then I have 4 squared as much energy. 16 times the original energy. 16 times 20 is how much energy I have. Okay? So that's kind of common on the Regents. On the multiple choice, so technically you don't have to show this work. You would just look at the formula, say, okay, double, square that, quadruple as much, 4 times 20, 80, answer. And that might be like choice B or something like that. Okay? If this makes you uncomfortable, you could go the long route, okay? And what you could do instead is you could take the data they gave you and plug in the 20 and plug in the 5 centimeters. Solve for K. I won't do it. You know, you just punch it on a calculator, you get the answer. And then take that K and use it again in the formula. Whatever this is, it goes right there for 10 centimeters, or 0.1 meters squared. And then you'll get 80, by the way. So you could do it out like that in 2 steps. Use the data, solve for K, use the K to solve for the answer. Okay? So if you would like, you could copy that down. I'll create a little pause here. Okay. Couple more examples. Maybe I'll lump them into one example just to speed things up. People like fast, right? So example 3, complete the graphs. Okay, so what if I created a graph like this? PE spring and X. And another graph I'll create is PE here and spring constant down here. Okay, a lot of students see this and they just sort of guess. They say, oh, okay, I know if I stretch the spring more, I'm going to get more energy, and I go like this, and that's wrong, okay? Whenever you get a graphical question and they ask you what the shape of the graph looks like, I always tell students, go to the reference table, find the formula. Okay, I won't bring this up to the camera because I already did, but you would find the formula like this, and you just jot it down. PE equals 1/2 kx squared. The formula tells you the shapes of the graphs. Notice when we look at the x dependence, we've got x squared. If I say y equals x squared, what does that look like? Most people could answer that. Parabola. So that's the correct answer. And again, you're not memorizing this. You should know that the shape, you always go find the formula on the reference table, and then it'll tell you what the shape is. X squared is a parabola. How about if I plot a graph with spring constant? What does that mean? Well, I'm going to keep x the same. So I'm going to stretch maybe this spring 10 centimeters. How much energy does that have? 10 centimeters, I plot the energy. I get another spring with a different spring constant. I stretch that 10 centimeters. And then I plot the amount of energy that it took to do that. So again, what does that graph look like? We're not memorizing. We look up the formula, which I already did. And notice there's no squared here. In fact, you could always put to the 1 power in a formula if you want. And when you're plotting something to the 1 power, like y equals not x squared, but y to the 1 power, that's a straight line diagonal. So there's another possibility. The formula will tell you it's a straight line because there's a 1 after k. Okay? And then the final example I'll do is just to kind of complete this graphical with another example. Let's suppose we did something from the last unit. We had acceleration and mass over here. And people say, oh, I don't know how that goes. Does it go like this? Does it go like that? Well, again, you're not guessing. You're looking up the formula on the reference table. And now, with m in the bottom, not on the top. If it were a equals f times m, that would be m to the 1 power. That'd be up like this. But this is not the formula. That's the formula. It's like a 1 over x graph. And if you look on your calculator, it's this descending curve like this. A lot of people do this when they see that. No, it's not a straight line. It's a descending curve when a variable's in the denominator. Again, reference table, find the formula. The formula will tell you the shapes of the graphs. All right, so that's it for today. The point is, when I lift something up, it's like recharging a battery, and then I discharge the battery, get that work back. Put the work in, get the work back. Or I could take a spring, put the work in, get the work back. The amount of work is given by that formula, okay? So, I hope you enjoyed today's physics video. I'll see you in the next physics energy video.